So the first reaction we're going to talk about in detail, and there's a lot of detail with this reaction, is the halogenation of alkanes with chlorine or bromine. We don't react with fluorine because it reacts too violently, and iodine is too slow. So these are the only two halogens we'll see. And like I said, this reaction's a little bit complicated. But we're going to start with the simplest version and then add layers of complexity. So the simplest version is that we can take a very simple alkane, like again, let's say cyclohexane, and react it with bromine and heat or light. Heat or light act as the initiators here, and here I'm going to use the Greek abbreviations. And what you end up having is you replace exactly one CH bond with a bromine. So what you get as your products are that you get a new CBr bond, and as your side product, you get HBr. So one of the bromines makes a bond with hydrogen, the other with carbon. And we generally only see a single addition, but that's not because this reaction only wants to do a single addition. It's because this happens, you generally use the alkane in excess. So there's a lot more alkane than there is bromine, and that stops you at one addition. You can do the same thing with chlorine, where you use chlorine and again, heat or light, and the same exact reaction will happen, except instead of having a new CBr bond, you obviously have a CCl bond. And again, your side product is HCl. Both of these reactions have the exact same mechanism. And so this is the first reaction we learned. It's interesting because it's a reaction of an alkane, which isn't something you see very often. Alkanes are very good for burning, combustion, but they don't undergo very many reactions. Now, like I said, in this class, we will often only replace one CH bond with a chlorine or a bromine. But if you change the conditions, you can get other options. So you could turn, if you use a lot of chlorine, you can turn methane, CH4. If you use excess chlorine and heat or light, you can turn that into CCl4. And as a side product, you get 4 molecules of HCl. But we're not going to deal with that. That's not really an interesting reaction because you could just buy CCl4. So that's not important for us. What's more interesting for us is the difference between reacting with chlorine and bromine. So if an alkane reacts with chlorine, it generally reacts with each CH bond in the alkene. So you have to find each CH bond, form a radical there, and put a chlorine there. Whereas bromine typically only reacts with the weakest CH bond in the alkane, which remember is the one that forms the more stable radical. So let's look at an example here. So if this is our example, we have 2 possible places where this can react. We have primary CHs. There are 6 of these, 3 on each of the end carbons, which I'm going to mark here in red. And there are 2 hydrogens on this carbon in the middle. And so the possible products we can form here are, we can react with the end hydrogen to put our chlorine here on the end of the molecule. That gives us 1 isomer. We can also react on the middle carbon to give us something that looks like this. This is another product. So we have 1 chloropropane and 2 chloropropane, and both are products that you're going to see. You also get HCl as a side product, which we'll mention. If you did the same reaction with bromine, you would only get 1 product, the product from the more stable radical. So with bromine, you would get HBr as a side product, but then the only product you would see is the one that comes from the secondary radical. So in the top example, you get a mixture of products. This is a 1-to-1 mixture to be more specific. On the bottom, you only see 2 bromopropane. So what I want you to practice now is the potential products with a new starting material. So this is your practice problem. Again, stop, think about it, and then we'll come back. So the easier one is the bromine. The bromine, we're looking for the most stable place to create a radical, and that's going to happen at the tertiary carbon. So there's a CH there. That's the hydrogen. That's the CH bond that's the weakest. That's the one that's going to be replaced with a CBr bond. And again, we always have the side product of HBr. And so that's also one of the potential products of the top reaction, but we'll have more products as well. So we want to go through and identify each individual unique hydrogen. So this carbon has 3 unique hydrogens. All of those will react with chlorine. This carbon has 2 unique hydrogens. Those will also react with the chlorine. We have the same hydrogen we saw for the bromine. And then this position here in yellow is the same as this position. If you don't believe me, we'll draw them and you can see. So we're going to have 4 different products, and that's not even getting to stereoisomers, which we'll talk about later. So here are our potential products: 1-chloro-3-methylbutane, 2-chloro-3-methylbutane, 3-chloro-3-methylbutane, and then these both are 1-chloro-2-methylbutane. The only difference between them is how we number. So this would be 1, 2, 3, 4. This would be 1, 2, 3, 4. But they're the same, so I wouldn't want you to write both of these on an exam. I would only want you to write one of them and know that they're both the same. So these are the answers. Now let's talk a little bit about the role of chirality in these halogenation reactions. So we first started with propane. When propane reacts with chlorine, you get 2 products, but neither product has a chiral center. So we're done. But if we look at the reaction of butane, again, this carbon is the same as this carbon. There are 6 hydrogens in total there that are identical. This carbon here is identical to this carbon. There are 4 hydrogens in total there that can react with chlorine. And what we end up with are 2 products. The first product is also achiral. So when you form this, there's no stereogenic center, no opportunity for stereoisomers. But our second product, the one where we react at the secondary carbon, that one does have the potential for chiral centers. So this one is chiral. Our first product is achiral, but our second product has a chiral center right there. And so what's going to happen here is that both enantiomers are going to form. So instead of forming this, what you want to make sure that you understand is that you're forming 2 enantiomers. One where the chlorine is coming out at us, and one where the chlorine is going away from us. These are the R and S enantiomers. We're going to talk about this more, the mechanism more in the next video, but the reason why this occurs is that the intermediate for this reaction is a radical, and that radical is planar. And so when it forms a carbon-chlorine bond, it can form it either on the front or the back. There's nothing to bias it towards one of those 2 sides. Now let's look at a molecule that's much more complicated. So here, again, I'm trying to make this a little bit simple, but in the realm of complicated molecules. So now we have a chiral center here already. And we're going to react this with chlorine. Again, with lighter heat. Again, we only have 2 places where this reaction can occur. One is here off this carbon, and there are 3 hydrogens that are identical off of this carbon. Because it has 3 hydrogens, in the product it will have 2 hydrogens and therefore will not be a stereogenic center. So here, we don't have a new chiral center, but the chiral center that's already there is still going to exist. So here, this bromine is still going to be pointing back because nothing's happened to that stereogenic center, and nothing will. We also have hydrogens here, and here there are 2 different hydrogens, one pointing out at us and one pointing back, and each of those are going to be replaced by a chlorine. So here we do have 2 new products formed. So in one, the chlorine will then be coming out at us, and in the other, the chlorine will be facing away from us. So I'm going to keep the methyl and the bromine the same in both cases. These chlorines, because they're identical, we don't use wedged and dashed lines, but you can assume that one is wedged and one is dashed. And this one is now going to be a dash, just so that it's the other stereoisomer. Now, if we call these three products A, B, and C, A and B are constitutional isomers, or structural isomers. They have different connectivity. A and C, structural isomers, different connectivity. B and C are not enantiomers because they are not mirror images. This second chiral center is the same in both. So B and C are diastereomers because they differ in their stereochemistry, but they are not mirror images. Remember these terms from Organic 1. The last thing we'll do here is another practice problem. So I want you to practice this, pause the video, then we'll come back. Hopefully you've paused. Here we have 3 different locations. We have the ends, then carbon 2, and carbon 3 in the middle. And what we end up with is 4 products. The product where 1 chloropentane and 3 chloropentane are both achiral, 2 chloropentane has a chiral center, and so you need to put both stereoisomers there.